This week we are going to be covering Module 6 on factoring. Now this is a very important aspect in algebra, as if you don't understand the factoring, the solving of equations and the more in-depth algebraic concepts will not go as smoothly for us. So I'm going to go through, we have several different types of factoring, and I want to go through all of those in short little snippets with focusing on one concept per little video. And we'll do lots of practice problems. So this is Module 6, Factoring. The first type of factoring that you should always look at whenever the directions say to factor is we should always look for the greatest common factor. This is a number that multiplies into all of our terms. Okay, once again, we're going to be using those terms and factors. We need to know those definitions. Terms are the stuff that's added, factors are the stuff that's multiplied. So we are looking for the greatest common factor first and foremost always in factoring. Let's go through some examples. In a problem like this, we want to know what goes into both 18 and 27. Now we could say that 3 goes into both of those. But 3 is not the greatest or the largest factor that they share. Think larger. Sure enough, 9 is the largest number that goes into both 18 and 27. So I'm going to be pulling out a 9. Now when we take out the greatest common factor, this is using our distributive property backwards. Instead of multiplying something in, we're pulling something to the front and writing the problem as a factors, or things that are being multiplied. Now 9 is the greatest common factor between the numbers 18 and 27, but we have variables, and variables can have common factors as well. The greatest common factor between x cubed and x squared is x squared. Can't pull out more than what you got, and I only have 2 x's being multiplied over here, so I can't take out more than that. Now, if I pull out the 9x squared, I'm taking the 18 and I'm pulling out or dividing out the 9, leaving me with a 2. I had 3 x's here. I pulled out 2 of them. That leaves me with 1 x left. So the first term, instead of being an 18x to the third, becomes 2x. Multiply it back in to make sure. 9 times 2 is 18. X squared times x. Multiplying like bases, we add the exponents. There's always a 1 up here. 2 plus 1 is our 3. Then we have our second term. Terms are separated by addition or subtraction. Have to put a plus sign to separate our terms again. 27 divided by 9, or pulling that factor of 9 out, leaves a factor of 3. X squared, pulling out both x squares, leaves me with no more x's left underneath. So this is your answer in factored form. It's in factored form because I have something times another quantity. Factored form. Let me talk a little bit more about those variables. The greatest common factor when it comes to variables is your smallest exponent. The greatest common factor when dealing with variables is the smallest exponent. The greatest common factor when dealing with your variables is going to be the smallest exponent, because that's the most that you can pull out is the smallest amount. Okay? Let's do another example. In this example, we have 2 numbers, 10x cubed minus 4x squared. The greatest number that goes into both of those, I always break them apart. I look at my numbers separately, then my variables. My numbers are 10 and 4. Those are both even numbers, and so the greatest common factor is 2. Once again, for my variables, the greatest common factor is the smallest exponent. So it's x squared. Don't forget the base number that goes with that exponent. If I pull out the 2x squared, 10 divided by 2 is 5. X cubed, I take out 2 of the 3, I'm left with 1. Minus 2. The x squares are gone. You can always check your factoring by multiplying back inside. 2 times 5 is 10. X squared times x is x cubed. 2 times 2 is 4. And the x squared comes along for the ride, and I still have my minus. So there's my answer for that one. Let's start another one. 6x cubed minus 3x squared plus 12x. Now here we just have a third term, but the same thing goes. The common factor has to be common in all 3 terms. It's all or nothing. So the greatest common factor of 6, 3, and 12 is 3. The greatest common factor of our variables is the smallest exponent, so it's that x, which is, once again, x to the first power. If I pull out, now remember when you're pulling out the 3, you're not subtracting it, we're dividing it to the front because we're doing the opposite of that multiplication or distributing inside. So 6 divided by 3 gives me a 2. I have 3 x's here, I take out 1, I'm left with 2. Minus, I took the 3 out, so I'm left with a 1, not 0. Whenever you're dividing, you're left with a 1. There were 2 x's, I took one of them out, so I'm left with 1x. Plus, 12 divided by 3 is 4. And I had 1x, and I took 1 out, so there's nothing left over. And we're done with that. Now let's do a little bit more of a challenging problem. Now this problem's a little bit scarier looking. It's really confusing and to see how many terms we have and what they are. You have to remember that the definition of a term is a number, a letter, or a product, or multiplication, of number and letters, or your variables, separated by addition. So in this problem, x squared is being multiplied by this ugly quantity, and then that term is ending because of the plus sign. So this is one term. Then I have 5 times this other quantity. Once again, that whole thing is one term of this expression. Now, in each term, we have different factors. In the first term, factors are the stuff that's being multiplied together. So what's being multiplied? I have x squared, which can be represented as x times x. And then it's being multiplied by this quantity. So this entire quantity, what's in the bubble or the parentheses, is one factor. The factor is x plus 3. I know this is where it gets confusing because this one factor contains 2 terms. But that's okay. This quantity is being taken times this first factor. So those are the factors of your first term. Of the second term, we have this 5, so that is a factor because it's times this quantity. So once again, we have 2 factors here, 5 and this x plus 3. So the question is, what's the factor that both terms share? And we'd say, aha, both terms have this ugly x plus 3. That is the common factor. So that is what I'm going to pull to the front. Now it was in parentheses here, it needs to stay in parentheses because that is the factor together, that whole quantity. So you need the parentheses there. If I take out the x plus 3 of this first term, what am I left with? The x squared. If I take out the x plus 3 in the second quantity, what am I left with? The plus 5. You need the plus sign to separate your terms. Now we are in factored form because it's this factor times this factor. Everything that we have left here is multiplication. That means it's in factored form. Let's try one more of those before we move on to our next concept. So once again, the first thing that we're looking for whenever the directions say factor is your greatest common factor. This problem, like our last one, has some ugliness to it. But what you should notice is that what's in parentheses is the same in both of our terms. This has an x minus 7, this has an x minus 7. That is what's common, so I bring it to the front. Now I only write that once. Remember, this is the reverse of our distributive property. When we multiply both things inside, here we say they have a common factor. I'm going to write it as one factor in front, and the distributive property takes care of the fact that it's in both of them. This is why it's a little bit more compact of writing it, because I only need that x minus 7 once. If I pull out the x minus 7, my first term I'm left with the 2x, and in the second term I'm left with subtracting 3. Now we need that subtraction to separate the terms. And that's our final answer. Taking out the greatest common factor is very beneficial because it allows our numbers to get smaller in case we have to do another step with them. Because some of these put things together like that, which you need more than one term, or more than one factoring to do to get to your final answer. So this is taking out your greatest common factor. And in our next video, we'll take an advancement from this into grouping when we have 4 terms. When factoring, the first thing I always look for is the greatest common factor. After that, we count how many terms. If we have 4 terms, then the method that we are going to use to factor that polynomial is a concept called grouping. Here's an example. If I have x cubed minus 7x squared plus 4x minus 28, I'm going to look for a greatest common factor first. And I notice that I have x's here, x's here, x's here, no x's there. A greatest common factor has to be common in all of the terms, not just some of them. I recognize that 7 times 4 is 28, but those don't have common factors as I can't take out a 7 out of a 4. And there's no greatest common factor when the number in front of your x cubed is a 1. So I know that I have no greatest common factor among these 4 terms. So that's when I use the concept called grouping. And what I'm going to do is I'm going to look at my first 2 terms and say, okay, if I just had these 2 terms, what's the greatest common factor there? I say, well, once again, I have a 1 in front of the x cubed and the negative 7. So there's nothing common among a 1, or between a 1 and a 7. But I have x's here and here. The greatest common factor with my variables is the smallest exponent. So I have an x squared that's common. If I pull out an x squared, what am I left with? Well, I took out 2 of the x's, I had 3, so I have 1 left over. I took out the 2 x's, so I'm left with the minus 7. Now I'm going to do the same idea with the second 2 terms. I'm going to group those 2 together and say, what's the greatest common factor between 4x and 28? The greatest common factor there is 4. Now it's a positive 4, and because I'm grouping 2 separate terms, I need to put that plus sign in to separate my terms, because I rewrote these 2 terms as the single term. Now I'm rewriting these 2 terms as a single term, taking out the greatest common factor of 4. If I take out a greatest common factor of 4, what am I left with? Well, taking the 4 out of here, I just have the x. 28 divided by 4 is 7. Nothing switched my sign. We're not done with this problem yet, because for a problem to be in factored form, your final answer has to be all multiplication. We have multiplication here, we have multiplication here, but they're being separated by addition. So we just simplified. We made 4 terms into 1, 2 terms, but they're still terms. I need my final answer to be factors so that the problem is done completely. But what you might notice is look at those ugly parentheses. The x minus 7 in both of them is the same. So I can do exactly what we did at the end of the greatest common factor section. I can take out that common factor of x minus 7. So my next step is to pull out this common factor of x minus 7. What am I left with? Well, the first term, if I take out the x minus 7, I'm left with x squared. And in the second term, when I take out my x minus 7, I'm left with the plus 4. Now it's a quantity times another quantity, so I am done. This is factored form. Let's do another one. Here's another example. Once again, the first thing I always look for is a greatest common factor. I don't see one again. I see, though, that I have 1, 2, 3, 4 terms, so I'm going to use my factor by grouping. That means, once again, I'm going to group the first 2 terms and take out the common factor. The greatest common factor is, in this case, x squared. What am I left with when I pull out an x squared? Well, I had 3 x's, I pull out 2, so I'm left with 1. Had the 2 x's, I pulled them both out, so I'm just left with the plus 5. If there was no number in front of there, I'd be left with a plus 1. You always have to have a term, as something there as a placeholder. Now I'm going to do the same thing with my second 2 terms. But what I notice here is that both of the terms are negative. Now I know when I factor by grouping that this quantity is going to be the same in both of them. And the quantity here has 2 terms that are both positive. But I have 2 terms that are both negative. So to turn those negatives, switch the signs around, my greatest common factor of those 2 terms will be negative. So what's common among or between a negative 2 and a negative 10 would be a negative 2. So my greatest common factor of these 2 terms is going to be a negative 2. So I indicate that by using my subtraction. Negative 2x divided by a negative 2, negative divided by a negative is a positive x. Negative 10 divided by a negative 2 is once again a positive 5. Remember that you can always check this by redistributing. This is not a 2 that's being distributed in, as we learned from last week, it's a negative 2. All subtraction can be turned into adding a negative. Negative times x is a negative 2x. Negative 2 times a positive 5 is my negative 10. So it checks out. Once again, now this quantity is the same in both of my terms. It will be. If it's not, you did something wrong. Okay, so now we can take it that next step and say, oh, what's common now? Keep going with your factoring and say, x plus 5 is what's common in both. So I'm going to pull that out and see what I'm left with. The first term I'm left with x squared. The second term I'm left with is minus 2. Can't go any further on that one, so we're all done. And that is how you do factoring with 4 terms. It's called factoring by grouping. Take your first 2 terms and your last 2 terms. Take out the greatest common factor, you'll see that you turned your 4 terms into 2 terms, and then those 2 terms will have this quantity that is identical. Pull that to the front. Remember, we only write that once. If they're not the same, you did something wrong. Right? Pull that to the front and see what you have left over. That's in your second binomial to say what's left over. Once again, that's factoring by grouping when you have 4 terms. To factor, I always start off by looking for the greatest common factor. After that, I count how many terms I have. If I have 2 terms, I'm always looking for the difference of 2 perfect squares. Now, in order to know what I'm looking for, I need to know what those words mean. In math land, difference means subtraction. So I'm looking for a subtraction of 2 perfect squares. Now, what are perfect squares? Well, perfect squares are any number that can be broken down to some number times itself. A perfect square can be written as some number times itself, because any number times itself, that would make a square, like a 2 by 2 square. Both sides are the same. So here's a list of the first 16 perfect squares that we should probably be aware of. Okay. If we're relatively aware of these numbers, looking for the difference of two perfect squares is a lot easier. 1 is a perfect square. 1 is the god of our math land, I call 1. It is a perfect square, it is a perfect cube, it is a perfect everything, because 1 to whatever power is still 1. Just a nice little side note. 2 squared is 4, 3 squared is 9, 4 squared is 16, etc. So I have the list here of the first 16 perfect squares. And then we also need to remember that x squared here at the end is also a perfect square, because that's what the square means, is it's x times itself. Any number times itself is a perfect square. That's why we call the little exponent of 2 a square. So let's look for the difference of perfect squares and see how that's going to factor. Here is an example of a binomial, 2 terms, that the directions will say to factor, that we have the difference of perfect squares. First of all, once again, we look for the greatest common factor. There's an x here, no x here. Here is a 4, so we have factors of 1, 2, or 4. But the number in front of x squared is a 1. Remember, there's always a number there. 1 times anything gives us anything. So between 1 and 4, there's no greatest common factor. So now we look to say, how else can I rewrite this as a product or a multiplication? And this is actually our FOIL method working backwards. That's why it's really important that you focus in on what the FOIL method is so that you can then go backwards this week. So if you recall, the FOIL method last week was rewriting our two binomials being multiplied together as a trinomial or a polynomial that you multiplied inside. Well, here we're going backwards. We're going to rewrite this as a product of 2 binomials. Writing it as a product of 2 binomials. All right, that's what our factoring is in essence going to be doing for us. Writing things as a product of 2 binomials. Now, you'll notice that we don't have that middle term on this one. That's actually beneficial to us, as what we're going to have instead is just our first and our last. And we can work this backwards. We can say what number times itself gives us x squared. We say, well, x squared is made up of x times x. And then we need to say, okay, what 2 numbers will multiply to a -4 and add to 0 since I don't have a middle term? Well, in order to get a -4, one of my numbers has to be positive and one has to be negative. Doesn't matter which one you put first, which one you put second. Now, 2 numbers that multiply to 4 but add to 0, if I use 1 and 4, that's not going to get me 0. The only way that we get 0 is if we add opposites. Same number, but one's positive and one's negative. And that's why we need a perfect square, because what number times itself, same number, gives us 4. It's 2 and 2. Now we have this in factored form. X plus 2 times x minus 2. Let's prove it to ourselves by foiling it to show what we get. Okay, this is our check. FOIL method. Take the first times the first. X times x is x squared. Then you do your outside. So really the FOIL method is taking this x and distributing it through. X times the -2 is a -2x. Then you do the inside and you distribute the same way. 2 times x, it's a +2, so this makes it +2x. And a +2 times a times a -2 is a -4 for your last terms. The middle terms are opposites. -2x plus 2x is not x, it's 0x. And 0 times anything is 0. So that term goes away. They cancel each other out. That's how you end up with just the 2 terms. We have the x squared minus 4. So there it checks. So what was the answer again? The answer is this product in factored form. Things that are being multiplied together is factored form. So x plus 2 times x minus 2 is equal to our x squared minus 4. And that's our factored form. Let's do another. If we have x squared minus 49, once again the first thing I look for is a greatest common factor. We don't have any here, so then I count how many terms I have. I have 2 terms. The first term is an x squared, that's a perfect square. My second term is 49. Now if you need to go back to your list of numbers of perfect squares, you can do so. And right there is 49. 1, 2, 3, 4, 5, 6, 7. 7 times 7 is 49. So that's a perfect square, and we are subtracting the 2 terms. So this is clearly the difference, subtraction difference of 2 perfect squares. So then I can factor it. It factors to the root of both of these. What do I do to get x squared? X times x. What times itself is 49? 7 and 7. To get a negative, I need 1 positive, 1 negative. It does not matter which you put first. You could put x minus 7 times x plus 7. The importance is that the quantities are in parentheses and that you have one of each sign. So either or would be correct for that one. Let's do a little bit more of a difficult problem. Once again, I'm first looking for the greatest common factor. I do not have a greatest common factor, so the next step that I look for is how many terms do I have? I have 1, 2 terms. So now I look to see if they're perfect squares. 81 is a perfect square. I have a difference. X squared is a perfect square, and 4 is also a perfect square. Every factor in both terms have to be perfect squares in order to factor by the difference of perfect squares. So I know that this is factorable. I make my 2 sets of parentheses. What times itself gives me a 4x squared? It's going to be a 2x and a 2x. What times what gives me 81? It's a positive 9 and a negative 9. And just like that, you have that factored. Feel free to FOIL the check. Here's another one to start looking at. Now, if we first of all go straight to the point that, oh, I have 2 terms and I'm subtracting, I must be doing the difference of perfect squares, we might miss something, because 27 is not a perfect square. And for that matter, 48 is not a perfect square either. You need to remember that whenever the directions say to factor, the first thing you always look for is the greatest common factor. It'll make your number smaller, easier to handle, and it'll let you go further in the factoring. So what goes into 27 and 48? Well, that's going to be 3. If I pull out a 3, what am I left with? 27 divided by 3 is a 9, and the x squared still comes along for the ride. Minus, how many 3's are there in 48? 16. So now I have a greatest common factor of 3 on the outside, and I have this binomial inside. Now the binomial inside is now the difference of 2 perfect squares. So I can go further. Now, this is not factored completely. This was just having the first step taken out. It's a product 3 times this entity, but it's not factored completely because I can go further with this. So what happens with the 3? Nothing, but don't lose it. It comes along for the ride. But I can break apart the 9x squared minus 16 into 2 binomials. I go through and say 9x squared is made up of 3x times 3x, and a negative 16 is made up of a positive 4 and a negative 4. Now I can't go any further because these only have x to the first powers, so now I'm done. Don't lose that 3, it's still part of my answer. So when factoring by group, when you're factoring with 2 terms, make sure that you realize that you have the difference of 2 perfect squares, but you might need to look for a greatest common factor first. Last problem that we'll do for this section of two terms. Once again, the first thing we're looking for is a greatest common factor. 49 is 7 times 7. That's not looking very good. And 144 is 12 times 12. So it doesn't look very good either. So now we can do ahead of the difference of two perfect squares, and we can break it apart. At this point, a lot of students say, oh yeah, sure, it's 7x minus 12 and 7x plus 12. But that doesn't give us a positive 144. Oh, then it's 7x plus 12 and a 7x plus 12. Well, try foiling that out once. Do you get 49x squared plus 144 as your final answer? Remember to do all stages of your foiling. Well, that gives me my 49x squared. The outside I have 7 times 12 is 84x. Inside I have another one of those, and then I have my 144. Now be careful. Does your middle terms cancel out in this case? Does 84x squared plus 84x squared make 0? No, this is adding. They're both positives. 84x plus 84x is 168x. Right? It does not give me 0x. So this is not factored correctly. Okay? Remember, you can only factor two terms if you have a difference or subtraction. Because this one's being added, you can't factor it further. It's already done. I think your book calls it prime. Okay? Because there's a plus sign, you cannot factor that further. Keep that in mind when looking through the two terms. You need to have a difference of two perfect squares. If you don't have perfect squares to begin with, maybe you have a greatest common factor. If you have a plus sign, you can't factor it at all, and it's done. And that is how you simplify factoring by two terms. Factoring trinomials. Now trinomials are the nice ones if they're in the easy form. We'll go through a bunch of problems when they are in the easy form of x squared plus bx plus c versus the not so easy form, which has a number in front of your x squared. Now this kind, the easy form, you really want to think back to how we FOILed previously. So last week when we FOILed, we had something like x plus 2 times x plus 3. This is our review of FOIL. And in order to simplify that, you took your first term and you distributed it through verse outside. Gave us x squared plus 3x, then the inside and the last, plus 2x plus 6, separating all of our terms nicely with our plus signs. And then we noticed that the middle terms, the oi of FOIL, were like terms. And so we then combined them and said, 3x plus a 2x would give me 5x. Plus 6 comes along, the x squared comes along. So what's happening this week is we're starting with the x squared plus 5x plus 6, and we want to rewrite it as this product of x plus 2 and x plus 3. Remember, in Mathland, it's all about learning how to go forward and then learning how to go back and undo what you just did. It's all about going forward and going backwards. So we're just going to start with this one. Now, if you think back to how we simplified things last week with the FOIL method, the first x times x gave us that x squared, and there were never any like terms with that x squared. That just comes along. And similarly, the last was a number times a number, which always gave you this plain old number or constant at the end, and that didn't have any like terms. So that just came along for the ride. It was the combination of the outside and the inside that made this middle term. And that outside and that inside came from taking the x times the 3, the factor with your 6, and the 2 in the x, the other factor of your 6. So working this backwards, thinking about working this backwards, we're starting with a trinomial this week, and we want to write it as a product of binomials. Now once again, we never had any like terms with the x squared, so the first terms here and here of your binomials will multiply to get you x squared. So we'll always go back to x times x. The last two numbers in your binomials multiply to your 6. So we need two numbers that multiply to 6. But at the same time, when we combine them, remember, they had to add to 5. So we're looking for two numbers that multiply to 6 and add to 5. Now we would say, hey, 3 and 2, and they both have to be positive. It doesn't matter which one you put first, the 3 or the 2. Alright. So that's not so bad. Let's see if that works on another. Here's another problem, x squared minus 12x plus 20. Once again, when factoring, the first thing I always look for is a greatest common factor. There isn't one that goes into all three of these terms, and so we go on to our next step. The next step says count how many terms you have. I have 1, 2, 3 terms, so this is a trinomial. Fortunately, it's also the easy kind of trinomial because the number in front of x squared is a 1. So that means I break it apart here to my two sets of parentheses. And I say, okay, the first one's got to multiply to x squared. So the first is always going to be x times x. Now I need two numbers that multiply to 20, but they need to add to a negative 12. This is a little different from our last one. Here we need two numbers that multiply to a positive, but add to a negative. Well, this is when I go to my signs and I say, what do I know about signs? Okay. If this sign is positive, okay, that tells me that both of my signs in the binomials have to be the same, because the only way to get a positive 20 is a positive number times a positive number, or a negative number times a negative number. So I know that both signs are going to be the same. Now, are they both going to be positive or are they both going to be negative? That's when I look to the number or the sign in front of my bx term. That's called the linear term. The sign in front of my 12 is negative, indicating that I need this to be a negative 12. Well, a positive number plus a positive number is not going to add to a negative number. Only a negative plus a negative makes it more negative. So this tells me that they're both going to be the same. This tells me that they're both going to be negative in my parentheses. Now, what numbers are going to go in there? We once again are looking for factors of 20, so two numbers that multiply to 20 that add to 12. Well, sometimes it's easier if we list all of our factors of 20. That's why we learned about factorizations. Let's see, 1 times 20 is 20, 2 times 10, and 4 times 5. Those are my only options for 20. Now, which combination adds up to a 12? We don't have to worry about the negative 12 in this case because the negative signs we've already placed in there that took care of that. And we see right down here that 2 and 10 make 20. Once again, because both signs in here are the same, it doesn't matter which number I put first and which number I put second. Now, make sure that you have the answer correct by foiling. Technically, in your FOIL method, you don't need to do the first and the last. I chose x times x to get me x squared. I chose negative 2 times a negative 10 to give me a positive 20. I just need to check that my outside and my insides combine to give me the negative 12. My outside here is a negative 10x. My inside here is a negative 2x. Negative 2 and a negative 10 is negative 12. So it checks. This is my answer in factored form. the quantity of x minus 2 times the quantity of x minus 10. Here's another example. Now it looks fairly similar to the first one that we did, that was x squared plus 5x plus 6, but we've switched both of our signs. Now I have to see how that's going to change our end result. Once again, there's no greatest common factor, so I go to my two sets of parentheses. Only way to get my x squared is x times x. Now in this case though, we have a couple other changes. I notice here that my sign in front of my 6 is negative. The only way that we multiply two numbers together and get a negative is if one is positive and one is negative. So when I put my numbers in, I'm going to have a positive and a negative. That means though that when I do my outside and my insides, I'll have one number that's negative and one that's positive. When I'm adding terms with opposite signs, we really subtract them. So in this case, I'm looking for two numbers that'll multiply to 6, but subtract and get me negative 5. Ooh, two numbers that multiply to negative 6, but subtract to give me my negative 5. Well, if I use 2 and 3, one of those would be negative and one of them would be positive. That would either give me a 1x or a negative 1x. That's not negative 5. So in this case, I'm not going to be using 3 and 2. Instead, we're going to be using our 1 and 6. The other option to get 6 is always 1 in itself. Now I need because it's subtracting to a negative 5, the larger number needs to be negative. So I'm going to put the 6 over here and the 1 here. And as always, I'm going to FOIL to check to make sure that I got it right. I don't have to check the entire FOIL method. Once again, I chose x times x to get me x squared. I chose a positive 1 times a negative 6 to give me a negative 6. I just need to check my outsides and my inside. 1 minus 6 is negative 5x. That's what I have here, so it checks. So because this was a minus up here, I knew I needed one of each sign. Because it was negative here, my bigger number needed to be negative. And then I was really subtracting. It was a 6 minus 1 to get me a 5. The 6 being larger, it stayed a negative 5. Be careful with your signs. So for the easy form of a trinomial, when we have x squared plus bx plus c, the key is to find two numbers that multiply to c and add to b. So you're going to ask yourself, what two numbers multiply to c and add to b? And as always, watch your signs. If c is positive, then both signs will match what b is. Let me say that one more time. If c, the constant at the end, is positive, then both signs in your parentheses will follow b. B is negative, so in this case, they're both negative. Then you're always looking for two numbers that multiply to 16 and add to 10. 16 is 8 times 2, and 8 plus 2 is 10. If the sign on your C is negative, that tells us that in our parentheses, we're going to have one of each sign. One's going to be positive, one's going to be negative. And we have to be careful as to which number we put where, because that will change our answer. In this case, I need two numbers that multiply to 20 and add, or because we'll have one of each sign, subtract to 1. Remember, there's always a 1 in front of any variable if there's no number written. I know that 5 and 4, my 5 is positive and my 4 is negative. 5x minus 4x is 1x, which is what I was looking for. So if I have a negative here, I have one of each sign, but be careful where you put your signs to get your final answer. That is factoring trinomials, which are in the easy mode. My next little video will be doing trinomials that have a number in front of x squared. That's going to be a little bit more difficult. Factoring trinomials in your not-so-easy form means that there's a number in front of your x squared. So we have a number a x squared plus bx plus c. We can no longer just pick two numbers that multiply to c and add to b, because there's going to be a number in front of your x here in your parentheses, and you have to decide, okay, how is that going to manipulate your outside and your inside? This is going to take some getting used to and a lot of practice. You get good at factoring if you practice it a lot. Practice, practice, practice. See how the numbers form. If you're not so sure about the factoring, go back to foiling in the last chapter and practice that, some of the uglier foiling ones, so that you can see where the numbers come from. There are some methods in your textbook about using all these different combinations to come up with your middle term, or try to separate it into 4 terms to do grouping. I don't need you to do any of that. For me, it was easiest just to guess and check. And as you do a bunch of these and you start looking at the numbers and feeling the numbers and seeing how they work together, you'll be able to come up with your answers a little bit faster. Let's go through some examples. Our first example is going to be 2x squared plus 9x plus 10. You see that we now have a number in front of the x squared that's going to affect our foiling and our checking of this. Go through the same steps though to get your first terms. What times what would give you 2x squared? Instead of it just being x and x, we need to take that 2 into consideration as well. The way that we get a 2x squared is 2 times 1. So 2x times 1x would give me a 2x squared. Now we go on and we do our same type of thought process as we did before. I need two numbers that multiply to 10, but the number that's over here, when we do your outside, is taken times 2. So this one's doubled in this problem because of the 2. And then you'll be adding it to your whatever your inside is. Well, the factors of 10 are 1 and 10 and 2 and 5. We know we can do something with our signs. This sign, if you recall, because it's positive, tells us that both of our signs in the binomials will be the same, because either a positive times a positive is positive, or a negative times a negative is positive. So then, since it's the same, we follow the sign on B. That rule has not changed for the harder type of trinomials. Since this is plus, both of my signs are going to be positive. So we're adding numbers together. That makes it a little bit easier. So now my choices once again for 10 are 1 and 10 or 2 and 5. If I put the 5 over here, 5 times 2 is 10. And then I have to add more to it. I'm not going to be able to get 9, as the 5 over here would already make it larger than 9 when I do my outside. So I'm not going to put the 5 over here. If I put the 10 over here for 10 and 1, I have the same situation. 10 times 2 is 20. That's way more than my 9. If I put it 1 and 10, well, inside here I already have 10x. So it's not going to be a 1 and 10 combination. Usually it's not. That's the little hint. When you have two choices of factors, 1 and 10, 2 and 5, most likely it's not going to be the 1 and whatever your number is. The exceptions to that is when 4 comes into play. 1 times 4 is used just as often, if not more so, than 2 times 2. But pretty much in all other numbers, if you have 1 in the number and a different pair, try the different pair first. So we said that the 5 is not going to go over here, because that would make 5 times 2 and make it too much. So let's put the 2 here and the 5 here, and see what happens when you FOIL it. Notice how I just mentally went through my combinations to see that, hey, I can't use a lot of those. So here I have 4x, and here I have 5x, and 5x plus 4x is 9x. That's what I was looking for. So this is my factored form of this trinomial. Here's another trinomial. Once again, the first thing that we want to look for is a greatest common factor. Is there a greatest common factor among the three terms here? 3 does not go into a 5, 5 does not go into a 12. No, there's no greatest common factor. Here's a hint. If there's no greatest common factor in the original problem, there won't be a greatest common factor in your factored form. Maybe I should write that down. Here we go. If there's no greatest common factor in the original polynomial, whether it's a trinomial, binomial, or something bigger, then there will be no greatest common factor in any of the factors when you're in factored form. So the little binomials will not have a greatest common factor in it. That can help you eliminate a lot of your options or your choices when you're guessing and checking for this harder kind of trinomials. So keep that in mind. If there's no greatest common factor in your original problem, there's not going to be a greatest common factor in any of your factors later on. Let's go back to that problem. Here I have 3x squared minus 5x minus 12. So let's make our two sets of parentheses. I'm going to go through and show some more thought process as we go through this one. Okay? Once again, to give us a 3x squared, I need 3x times x. Now in this case, I have a minus 12. That means that one of my signs will be positive and one of them will be negative. I don't know which one's going to go where. I'm just going to throw in a positive and a negative and hope for the best. I guess we'll do negative and then a positive. Now, the nice thing is, when I do my FOIL to check, my outside, my insides, if I get a positive 5x instead of a negative 5x, all that means is my signs need to switch around. Okay? If I do my outside and my insides and I get the right number up here but the wrong sign, just means I need to switch my signs around. So let's go through and list all of my options for 12. I could use 1 times 12. I can use 2 times 6. I can use 3 times 4. Now I'm going to go through, even though I have these nice little markers, and see what I can and can't put in there. Now, as I stated before in the last example, chances are it's not going to be 1 times 12. So I'm not even going to choose that right away. If my other options don't work, then I can go back to that. But most likely it's not going to be 1 times 12. So I'm not even going to use that one right now. So I'm going to go to 2 times 6 and see if that works for me. Now, if I put the 6 first, notice here, I would have a greatest common factor of 3. Now, I would be able to pull that out. But as I just stated before, if there's not a greatest common factor in your original problem, there's not going to be a greatest common factor in either one or the other of your factors. Because remember, when we're in factored form, this is equivalent to your original problem. If there's a greatest common factor here that you could then pull out, that's not the same as what our original problem is, because the original problem does not have a greatest common factor. So that tells me that I cannot put a 6 there, because then I would have a greatest common factor. And since I don't have one up here, I'm not suddenly going to have one down here. So that takes care of one of my choices. So I'm going to make that into the 2 instead and put the 6 over here. And now I FOIL to check. Once again, I don't have to do the F of FOIL because I put 3x and x in there to get me 3x squared. I don't have to do the L of FOIL because I chose a -2 and a 6 to get me the -12. I just need to check outside and inside. So outside gives me 18x. Ooh, that's big. Inside I have -2x. -2x plus 18x is 16x. I'm looking for a negative 5. So that tells me that this is wrong. So let me try another pair. As I stated before, I can't put this in the other order of a 6 and a 2, so that option is completely out. So I have to go back to my 3 and 4. Now, if I put 3 in first, once again, I would have a greatest common factor of 3, and I can't have that. So I've got to try my 4 first and then my 3. Now I do my outside and my insides to see if I get my negative 5x. Outside here, positive times a positive will give me a positive 9x. Inside I have a negative 4x. Negative 4x plus 9x is 5x. But it's positive because 9 is positive. However, in my problem, I need a negative 5x. So I have the right numbers here, but I have the wrong signs. Just have to switch the signs. So the positive is going to go on this side, and the negative is going to be on that side. Now let me double check to see so I can prove to myself that I have the right answer. 3x times the negative 3 is a negative 9x. Positive 4 times positive x is a positive 4x. If I have $4 and I take away $9, now I'm suddenly $5 in the hole. That gives me my negative 5x. So the answer to factoring 3x squared minus 5x minus 12 is 3x plus 4 times x minus 3. I hope that that helps you with your more difficult types of trinomials. Like I said, make sure that you practice them a lot. And always look to see if you have a greatest common factor that you can factor out first. If you don't in the original, then you're not going to have one later. So that's going to eliminate some of your options for you and make it a little bit easier to go through the remaining options. Practice a lot of them. Foil to check. There's no reason to get factoring wrong, as you can always foil to check. Now, we'll finish up this by going through a video on why do I need a factor anyway? So the question always occurs, this isn't an easy chapter of factoring. Why do I need to do this anyway? Why do I need to learn how to factor? And factoring is a great tool in Mathland. It allows us to solve bigger, uglier, scarier types of problems. Because if we have a large polynomial and we can factor it, we can then solve that equation, find the zeros, which are really important when you're doing higher level of mathematics. Now, we're not going to be doing higher level of mathematics, but it's still good to know your foundation. This allows us to solve bigger, badder things. It also allows us to simplify bigger, badder things, as we're going to find out next week when we stick rational expressions, which are fractions, and factoring together. You need to know the factoring this week to do next week's. Then we get a little bit of a break, but factoring comes back for the last 2 weeks as well, when we're solving radical equations and when we're solving quadratic equations in the last week before the final. So that's why we need to know how to factor. We're going to be able to solve stuff. How are we going to solve stuff? Well, this is the great thing, because to solve by factoring means that we get to use my favorite property, the zero product property. The zero product property is a very simple property. I think your book actually calls it a law, but I like the alliteration with product property together. It makes more sense to me. But the zero product property is a very simple property, and it allows us to do so much in Mathland, and that's what's exciting about it. All right, you guys might not agree, but I think it's fantastic. And it's so simple. This is what it starts with. It simply says, if you have two numbers, A and B, multiplied together, so it's a product, multiplication, and it's equal to 0, thus it's called a zero product, product that equals 0, something has to happen there. Now let's think about when we learned our multiplication tables. Any number times 0 was always 0. And 0 times any number is 0. So if I have two things being multiplied together equal to 0, then I know that either A has to equal 0, because 0 times some number is 0, B has to equal 0, as some number times 0 is 0, or they're both equal to 0, as 0 times 0 is 0. That's simply what the zero product property says. If I have two numbers multiplied together equal to 0, then I know one of the two factors has to be 0. One of the two factors, the stuff that's being multiplied together. Let's see this with ugly variables. Say I have a problem like this. X plus 2 times the quantity of x minus 5 is equal to 0. My expression on the left side is already what we call in factored form. It's being multiplied together. And we're set equal to 0. This is different than what we did before because there's an equal sign. So this is an equation because there's an equal sign. It's now a balance. What we did before was simplifying expressions. We're just playing with those expressions so we can see how they work once we get them into an equation, as we do have now. So I have two numbers that are factors, meaning that they're being multiplied together. This is a product. This right here is that A, and it's being times this value right here, which is B. So I have A times B equal to 0. So I have the exact initial setup of the zero product law, or the zero product property. Two numbers being multiplied together equal to 0. Then according to the property, either A is 0, B is 0, or both. So I need to ask myself, what value of x will cause, not because, but cause and effect, cause my A to equal 0? Because A has to be 0. So what's going to cause x plus 2 to equal 0? Well, now this is a little equation. It's a linear equation because our x is to the first power, and we should know how to solve this one at this point. To get the x by itself, we'd simply subtract 2 from both sides. So x equals -2. Well, let's plug that back in. If x was -2, I would have -2 plus 2, and here I would have -2 minus 5. -2 plus 2 is 0, times, well, that's a -7, but 0 times anything is 0. So my left side would equal my right side of 0, and so it's a solution. X equals -2 is a solution. Aha, but it's not the only solution, because the property says that if I have a product like A times B is equal to 0, either A is 0, as we just found, or B is. So what's going to cause the x minus 5 to be 0? Set that equal to 0 to find your second solution. X minus 5 equals 0. To get x alone, so it's solved for, you add 5. Whatever you do to one side, you do the other. Since it's the opposite operation, we end up with x is equal to 5. Well, let's check that back in here. If I have 5 plus 2, let's squeeze that in down here. That gives me a 7 times 5 minus 5. Well, 5 minus 5 is 0. So 0 times anything is going to give me 0, which makes the left side equal to the right side, which means it's a true statement. which means it's a solution. So I have two solutions to this problem. X is equal to -2 or x is equal to 5. Those are the two solutions that we were able to get because our equation was already in factored form. Let's try another one. What if I had the quantity of 2x plus 5 times the quantity of 3x minus 1 is equal to 0? Because it's already equal to 0, I'm already in my property form, the zero product property, which states that either the A or the B has to be 0. So once I see that I have a quantity times another quantity equal to 0, I know that I can set the factors. Factors are the stuff being multiplied together. So this is a factor. This is a factor. I can set the factors separately equal to 0 and solve. That's the shortcut way of thinking about the zero product property. So 2x plus 5 would equal 0, or my 3x minus 1 would equal 0. So now I have a smaller problem, a linear equation. These are our two-step equations that I solve separately from each other. This is one equation I solve. This is the other equation that I'll solve. To solve this, we know that we have to get the term with the variable by itself and get rid of any constant or term that does not have the variable. To get rid of adding 5, we subtract 5. Whatever you do to one side, you do to the other side. 5 minus 5 cancels, which is why we did that. 0 minus 5 is a -5. Then to get x by itself, we have to get rid of the 2. 2 and an x mushed together means multiplication, so to cancel multiplication, we divide. 2 divided by 2 is 1. 1 times x is x. On the other side, we don't do the division here. We leave it as a reduced improper fraction, always. Never mixed numbers, and don't do a decimal. We don't like them in math land. So that's our answer, -5/2. It's less work this way. You didn't have to go to a handy dandy and type it in to get a decimal. You didn't have to do anything else. There is your answer from that side. However, don't forget you have a second one that you have to solve. Here it's 3x minus 1 is equal to 0. Once again, we get the term with the variable by itself by moving the other term by adding or subtracting. Because it was a subtracting one, we do the opposite operation, which is to add 1. And you do it to both sides of your equal sign to keep it balanced. A negative and a positive make 0. 0 added to anything is anything. And now to get our x by itself, we once again have to do the opposite of this multiplication, which is division. 3 divided by 3 is 1. 1 times anything is anything. And there's our answer once again on the other side, 1/3. So our two solutions, x is equal to -5/2 or x is equal to 1/3. Once again, you can plug those back in to your original problem and show yourself how the left side equals the right side, and that's what makes it a solution. It keeps a balanced or a true statement in our original problem. So here's another problem. It's still an equation, so we are still solving it without even having to see the directions because there's an equal sign. However, in this case, our problem is not in factored form. We have a trinomial or 3 terms on the left side of our equal sign. The good news is the equation is already set equal to 0. If it's not, the first thing we would have to do is add or subtract any terms from one side and move it all to the other side so that our equation is equal to 0. You have to have an equation, and it has to be equal to 0 to use the zero product property. We don't have a product at this point, so that's why we have to learn how to factor, because we do not know how to solve when we have an x squared and an x. We cannot combine those two terms because they are not like terms. Like terms have the same variable raised to the same power. This has an exponent or a power of 2. This has an exponent or a power of 1. Whenever there's nothing up there, there's always a 1, because the God of Mathland is always with us. So we cannot combine those. So how do you get x by itself when you have an x squared and an x? That's why you need to know how to factor. So we break it apart. We have three terms. First thing we look for is a greatest common factor. We don't have one here. We have 1, 2, 3 terms, so we make our two sets of parentheses. Do not forget that it's equal to 0. It starts off as an equation. It ends as an equation. What times what gives me the x squared? X and x. Oh, lucky you guys, it looks like I have an easy problem here. Negative 10, a negative tells me I need one of both signs, so it's a positive and a negative. Doesn't matter which one you put first in this problem because we have x and x. So I need two numbers that would multiply to 10 but subtract to a negative 3. Well, that's going to be a positive 2 and a negative 5. Negative 5x plus 2x is a negative 3x. Right? So now I'm in factored form. Now I have one factor times another factor is equal to 0. That's my zero product property. So now we can do what we did in the last examples. Set the factors separately equal to 0 and solve. Once again, I made it fairly easy on us by making it a simple one-step problem here on both of them, so we can come up with our answer a little bit faster. Those are our two solutions. Either x is equal to negative 2 or x is equal to 5 to solve for this equation. So your steps for solving this week is to make sure that you set your equation equal to 0, and that's by subtracting or adding terms all to one side. Then you factor completely, set those factors equal to 0 and solve it. That's that zero product property. And then check. Show all of your work in solving to make sure that you didn't make a sign boo-boo. We like to just assume things and then we get the signs wrong. So make sure that we check and that we're actually showing all of our steps in solving so that we don't mix up our signs. And then of course, check back in the original, make sure that the left side equals the right side. And that is why we learn how to factor.